Welcome back to the Deep Dive. Today, we are opening up a massive technical report on a brand new vision language model series, Qwen3-VL.
Yeah, and this isn't just a minor update. The report really positions this model family as the most advanced VLM in the whole Qwen ecosystem.
So our mission for this deep dive is to really get into the nuts and bolts of how they engineered this leap. We'll be looking at the architecture, the training process, and of course, the benchmarks.
And it's a whole family of models. They've released dense variants from, 2B all the way up to 32B parameters, plus these highly optimized mixture of experts models.
Including that flagship 235B model.
Yeah.
So there's something tuned for just about any quality or latency need you might have.
Right.
Now, the report is very clear about three core pillars that are supposed to define this model's superiority. First, and this one caught my eye, is markedly stronger pure text understanding. They claim it can actually surpass some comparable text-only models.
Which is a huge claim, right? It suggests that all the multimodal training didn't actually hurt the language core.
The second pillar is robust long context comprehension. We're talking a native context window of a staggering 256,000 tokens.
And that's for interleaved multimodal inputs. That's foundational for handling things like long videos or, massive documents.
And the third pillar is advanced multimodal reasoning. This is where they're claiming top performance on really tough evaluations like MMMU and those visual math challenges.
Like MathVista, yeah. It shows it can reason across a single image, multiple images, and video.
Okay, so let's start with the architecture. What are the specific components that let them handle that much context and that kind of reasoning?
They made 3 key structural enhancements, and they seem to be targeting spatial and temporal modeling. The areas where VLMs tend to struggle as context gets longer.
And the first one is an improved positional encoding scheme.
Yeah, they call it interleaved MRO-P.
I remember the last version, 2.5-VL, used a standard MRO-P that kind of chunked the dimensions into temporal, horizontal, and vertical groups. The report said this created an imbalanced frequency spectrum. What does interleaved fix?
Well, think of it this way. If you put all your low-frequency sounds in one speaker and all your high-frequency sounds in another, the mix gets muddy.
Okay.
The previous model was sort of doing that with the data. It put all the temporal movement information into one specific processing band. Interleaved MRP spreads those components temporal, horizontal, and vertical uniformly across all the frequency bands.
So it's a much more even distribution of the representational load.
That's it. This balancing act significantly reduces that original bias, and the result is much more faithful, long-range positional modeling, which is just critical for tracking things accurately across a long video.
The second innovation is something called deep stack integration.
Yeah.
This sounds like it's about getting more visual detail deeper into the model.
It is, and it addresses a major limitation. Usually, the vision transformer, the VIT, processes an image, and only the final, very compressed visual tokens get passed to the leverage model.
Right.
DeepStack changes that. It injects visual tokens not just from the final VIT layer, but from intermediate layers as well.
So it's tapping the stream earlier.
Exactly. They're fed directly into corresponding layers of the LLM using these lightweight residual connections.
That seems really important. If you only get the final output, you're getting high-level concepts like a cat on a couch. You lose the fine-grained data, like where the cat is precisely on that couch.
And DeepStack keeps that richer detail alive. It preserves that multi-level visual information. And the report makes a point to say this is done without actually increasing the context length, so it's efficient.
And the third piece of the architecture goes back to video. They moved away from absolute time alignment.
They did. The old model used sparse temporal position IDs. Now, with Qwen3-VL, they've shifted to explicit textual timestamp tokens.
So the model literally sees something like 3.0 seconds in the input.
Yes, prefixed right onto the temporal patches. It's a simpler, more precise way to represent time, and it's invaluable for tasks like video grounding where you need to find something at an exact moment.
With an architecture that complex, I imagine training it was a challenge. Did they have to balance these new vision goals with, maintaining the text quality?
They did, and they mention a critical optimization, applying square root reweighting to the training objectives. They found this was the best way to balance the text-only learning with the new multimodal goals.
And it worked.
Seems so. It boosted multimodal performance without hurting the LLM's core text capabilities.
That brings us to the pre-training structure itself. This is where they built up to that 256K context window using a really comprehensive 4-stage pipeline.
It's very systematic. It starts with stage 0, which is just vision language alignment. This is a shorter phase, 67 billion tokens at an 8K sequence length.
And they keep parts of the model frozen here.
Yeah, the LLM and the vision encoder are frozen. They only train the MLP merger layer, which is like the computational bridge between the two. It's a very efficient first step.
So you get the two main parts speaking the same language before trying to train the whole thing.
Right. Then stage 1 kicks off full multimodal pre-training. Everything is unfrozen. This is a massive 1 trillion tokens, still at 8K sequence length, but now with really diverse data, including some initial video.
Okay, then stage 2 is the big leap, long context pre-training.
This is where they quadruple the sequence length to over 32,000 tokens, another 1 trillion tokens of training. But here they adjust the data mix to really focus on long-form text and a lot more video and agent data.
And then the final step, stage 3, ultra-long context adaptation.
This is where the sequence length is pushed to its max, over 262,000 tokens. It's a shorter phase, using 100 billion focused tokens that are curated specifically for long video and long document tasks.
That progressive scaling seems really smart. But that last stage, even at 100 billion tokens, must require an immense amount of compute.
It does, but the fact that they only used 100 billion focus tokens instead of another trillion shows they were being strategic with the compute budget. It suggests that once that foundation is laid, the final adaptation can be done more efficiently.
Beyond the pipeline, the training data itself got a major overhaul. I saw a huge expansion in multilingual OCR.
It's a huge jump. The previous model supported 10 non-English or Chinese languages. Qwen3-VL supports 39 languages. And they didn't just scrape data. They synthesized a corpus of 30 million multilingual OCR samples to make sure it was robust.
That move from 10 to 39 languages completely changes where this model can be used. It makes it far more viable for global document processing.
For sure. They also refined the grounding. For bounding boxes and points, they adopted a normalized coordinate system scaled from 0 to 1,000.
And the report says that helps with robustness.
A lot, especially when you're dealing with all the different image resolutions and aspect ratios you find in a massive data set.
We're also seeing some very specialized data being created, new data sets for spatial reasoning and even 3D grounding from single images.
And really key for modern uses, they integrated multimodal coding data. So the model is trained to do things like convert a UI screenshot into HTML and CSS.
Okay, so before we get to the results, the report mentions this post-training process where they split the model into non-thinking and thinking variants.
Correct. Both versions go through supervised fine-tuning, or SFT, and a strong tweak distillation. But the thinking model gets additional reasoning and general reinforcement learning to really sharpen its instruction following and reasoning.
Let's get to the results then, because this is where all that engineering should pay off. The flagship model, the 235B MoE, seems to be a real powerhouse.
It is. The thinking variant achieves state-of-the-art results on tough reasoning benchmarks like Math-Vistamini and VisiLogic. It shows its internal problem-solving mechanics are very strong.
And what about for general instruction following?
For that, the same model got the best overall score on MIA Bench with 92.7. That shows a superior ability to execute complex, multi-step instructions without errors.
But the part that really validates the training pipeline for me was the long context test, that needle in a haystack evaluation for video.
The results there are pretty remarkable. The Instruct variant achieved 100% accuracy on videos up to 30 minutes long.
Which lines up perfectly with its 256K token context window.
It does. It means it can find a specific piece of information placed anywhere in that huge stream with perfect recall.
And then they pushed it even further.
They did. They extrapolated the context all the way out to 1 million tokens, which is about 2 hours of video. And even then, it maintained an accuracy of 99.5%.
That level of robustness at such an extreme length is, well, it's very rare.
It is, and it proves that the architectural changes like interleaved MROP and the long context training really work to prevent that catastrophic decay you sometimes see.
The data overhaul also paid off in document processing, right?
Clearly. The Instruct model set new SOTA records on OCR-focused parsing benchmarks like CC-OCR and OmniDocBench.
And that big multilingual push.
It was a success. The model achieved over 70% accuracy on 32 of the 39 supported languages on their internal test set, showing that the investment in synthesized data was very effective.
There's one last really interesting finding from the fine-grained perception section. They compared the performance gains from just making the model bigger versus integrating external tools.
Yeah, like an image zoom function.
And the finding was pretty definitive. The performance gains from using tools consistently outweighed the gains from just increasing model size.
They even quantified it. They saw a consistent gain of about 5 points on the V benchmark across the entire Qwen3-VL family just by adding tool integration.
So that really validates their choice to focus on agentic learning and not just brute force scaling.
It does. So at the end of the day, what we have with Qwen3-VL is a comprehensive technical leap. You have major architectural innovations like DeepStack and Interleave and Rope combined with this meticulous multi-stage training pipeline.
And the result is a flexible family of models, both dense and MOE, that can handle these extreme long context tasks with state-of-the-art reasoning.
The report itself really frames Qwen3-VL's role as a foundational engine for complex, real-world workflows, things like image-grounded reasoning, agentic decision-making, and multimodal code intelligence.
The dedication to refinement is really what stands out. So maybe the final thought here for you is to reflect on what the report implicitly tells us about performance. The fact that they committed so many resources to the post-training refinement, the SFT, and the reasoning RL suggests that even after you've achieved massive scale, the most powerful performance gains might not come from the parameter count itself, but from that deliberate final optimization of the model's ability to follow instructions and to reason.